Hello viewers. English mathematician Isaac Newton and German mathematician Leibniz are usually credited with the invention of calculus. But earlier mathematicians, including several Indian ancient mathematicians, also explored the concepts of rates and limits. Today, calculus has invaded every scientific endeavor. You can find its use in physics, chemistry, biology, economics, sociology, engineering, of course. Calculus helps us to understand the structure of a rainbow, teaches us how to make more money at stock market, and of course guides a spacecraft. Today we begin our explorations with application of derivatives, starting with problems of tangents, which puzzled even Isaac Newton and Leibniz in 1600. What does tangents and normals have to do with derivatives? Let us take a look at it through an applet. Here we have a graph of the quadratic function. Let us take a point A on this graph and construct a tangent at the point A. Let us also measure the slope of this tangent. In this position, the slope of the tangent is represented by the number b, which is taking the value 2. Let us also construct a point P which has the coordinates same as the x coordinate of the point A and the slope b as the y coordinate. Note that as I change the position of the point A, the position of the point B also changes. You can see that it is leaving a certain trace behind, and also there is a certain relation between the x coordinates of the point P, which you can see resulting in a certain list on this table that is on the right hand side. Now, I am going to again move the point and you observe and decide what the relation is going to be. So, as you move the point A, these values very quickly change, but you can keep an eye on them and see that there is a certain relation present on the x and the y coordinates of the point P. Can you guess what that relation is? Yes, definitely y is equal to 2x as far as the coordinates of the point P are concerned. And that is exactly what is the derivative of x square, right? So, what does that all mean? What we have just shown is a representation of a fact which has been said again and again, that derivative measures the slope of the tangent to the curve at any point. So, what is derivative of a function? It measures the steepness of the graph, so it is a slope. Also, it is the slope of the tangent line to the graph of the function at the given point, and it is slope of a secant line, that is the line which is connecting 2 points on a graph in its limiting position when it becomes the tangent. So, in the limiting position, when the 2 points come closer to each other, we get the slope of the tangent, which is also what we understand as the derivative. Once this is understood, what we need to figure out is how to find equation of the tangent to the curve at a given point. So, what we have just now discovered is that the slope of the tangent to the curve at the point x1 y1 is the value of the derivative at that point. So, it can be represented as dy by dx at x1 y1 or f dash at x1. So, the equation of the tangent to the curve y equal to f x at the point x1 comma y1 is y minus y1 is equal to dy by dx at x1 y1 into x minus x1, coming off from the simple slope point form of the straight line. equation of a line is y minus y1 equal to m times x minus x1. Also we have equation of normal to the curve at a given point. We have the slope of the normal at the point x1 comma y1 to the curve y equal to fx given as minus 1 by dy by dx at x1 y1. Why? Because the normal is perpendicular to the tangent at the point of contact, and therefore the equation of the normal to the curve is simply y minus y1 equal to negative 1 upon dy by dx at x1 y1 into x minus x1. This is something very straightforward. At the same time, what you need to be careful with is to form equation of a line, in this case tangent, you need two important quantities, the point and the slope of the tangent. Once these two are known, we are ready to face any situation. Here's a simple question to begin with. Find the equation of tangent to the curve y is equal to x cube minus x plus 1 at the point whose x coordinate is 2. So, as I said just now, to begin with you must know the point at which the tangent is to be constructed, that is x1 comma y1. Since it is a point on the curve, when x is 2, y can be calculated by putting the value of x as 2 in the equation of the function. Dy by dx is 3x square minus 1. So, the slope of tangent at 2 comma 7 is nothing but the value of dy by dx at 2 comma 7, resulting in the number 11, and therefore, the equation of the tangent to the curve using the point slope form would be y minus 7 equal to 11 times x minus 2. Simplify, express as a linear equation in the standard form ax plus by equal to c. We have another problem where the information is indirect. Find the equations of the normals to the curve y equal to x cube plus 2x plus 6, which are parallel to the line x plus 14y plus 4 equal to 0. So, what you are given directly or indirectly is the line is such that the normal to the curve is parallel to it. So, slope of line will be same as slope of normal. You know the slope of normal. What is the second thing that you need? The point of contact. So, our main work would be to get that point of contact through the given information. Starting off with therefore, the unknown, let x1 comma y1 be the point of contact at which the normals to the curve are parallel to the given line, and therefore, the slope of the line, which was minus 1 by 14, will become the slope of normal to the curve at x1 comma y1. Also, we know the slope of the normal is negative reciprocal of the derivative at that point. So, let us find the derivative, which is 3x square plus 2. Therefore, the slope of normal in terms of derivative will be negative 1 by 3x1 square plus 2. Equating the two quantities, what we had and what we have found out, I get a relation in x1 giving me two values of x1, and therefore, there will be two values of y1 since x1 comma y1 lies on this curve. So, I get 2 points at which the condition is being satisfied as 2 comma 18 and negative 2 comma negative 6. So, that is why in the question asks for normals to the curve. There is a plural word here. So, I need two normals. I have two answers for this question. The normal at 2 comma 18 with slope negative 1 by 14 will turn out to be x plus 14y minus 254 equal to 0, and the second normal turns out to be x plus 14y plus 86 equal to 0. Something which was indirect, but we could figure it out because I had a known and an unknown linked together through the concept of normal slope being the negative reciprocal of the derivative of the function. Another question, an important one. One more important question for you. Pay attention to the statement. The question says find the equation of normal to the curve x square equal to 4y which passes through the point 1 comma 2. What is significant and what is risky about this question is the tangent normal are constructed at a point of the curve. So, here the normal is passing through the point. This point is not the point of contact between the normal and the curve. So, you cannot use this directly as your x1 comma y1 and then proceed with finding the derivative at this point. So, that is one important information for you to pay attention to. So, the point of contact is still unknown. Let us begin with that as x1 comma y1. So, if x1 comma y1 is the point of contact, derivative gives me x by 2. Therefore, the slope of normal at x1 comma y1, which is the negative reciprocal of derivative at x1 y1, will be negative 2 by x1. This results in an understanding of slope as a quantity which is still unknown. I have to equate it with something else to get the value of x1. So, what is the other information that we have? The normal passes through the point 1 comma 2 and it also is passing because it is at x1 comma y1. So, I have 2 points through which the normal passes and therefore, the slope of normal using our 2-point form would be 2 minus y1 upon 1 minus x1. So, I can equate it with negative 2 by x1, but I can make it first a function in one unknown by replacing y1 with x1 square by 4, because x1 square was 4 times y1. x1 y1 lies on the curve x square equal to 4y, right. So, we are ready to simplify and equate with negative 2 by x1. What is left is simplification. Cross multiply, something simplifies, cancels out, gives you x1 as 2. Once I have x1, using again the expression that x1 square is equal to 4 times y1, I get y1 as 1. Therefore, the point at which the normal is constructed has the coordinates 2 comma 1, slope of normal which was negative 2 by x1 takes the value negative 1. So, I have the point, I have the slope and therefore, the equation of normal y minus 1 equal to negative 1 times x minus 2. Simplify and express it in the standard form, I get the equation of normal as x plus y equal to 3. So, with this we end today's lesson on tangents and normal. I hope this has helped to clarify some of your doubts. Thank you for watching.